me begin with a word of prayer. So, dear Heavenly Father, we thank you for this morning, and thank you for these students. Just ask you to bless our work today, help us to glorify you in what we do, and I just pray that all the students would have the courage to ask good questions as they have them, and just help us to understand your creation a little bit more today, Lord. In your name I pray, Lord Jesus. Amen. So, so you guys have had a couple minutes to work on these. Let me just kind of go through them one at a time here. I guess I probably should start by tracing over them so you can actually see them. Sorry, this red marker that's in the classroom is kind of sad. So how can we solve this one? What do you guys want me to, what should I start with here? Add 2, okay. Then what? So at this point, we can either divide by 3 or we can take the natural log. What do you guys want to do? Divide by 3. All right, sounds good. 10 to the x equals 22 divided by 3. Now we could use log base 10. We could use natural log. Let's do log base 10 here, yeah. So log base 10, right, which is the common log. We just write log 4. Right? But then, since we're doing log base 10 of 10 to the x, we just get back x, right? So there you go, that's the answer. X equals to the log of 22 over 3. So if we want an exact answer, that's it. Now, we can find the decimal approximation for that, right? We get out our calculator. So what is the decimal approximation for this answer? I get 0.8653 approximately. So there you go. Any questions about this one? So let's call this example 1. See here, here's example 2. So if you guys are just getting here, these are ones I wrote up on the board before class because I was a couple minutes late to class. I fell prey to the CFA parking. I forgot CFA is upon us again. None of your CFAs, right? No, I didn't think so. They're not here yet, right? They're here? Oh, they're here tonight, okay. Say they're here, that's kind of, it's more scary. Let's see here. How about this one? How should we solve this problem here? What should my opening move be for this one? What do you guys think? Distribute? What do you mean? I mean, you do not mean, surely you don't mean this, right? No. Okay, good, because that is a lie. Okay, this is no. Never ever do this. That's not the case. So, what do you mean by distribute? Do you mean, can I combine these logarithms in any way? Should I take the exponential of both sides? What do you think? I think we should combine the logarithms, right? So, yeah, you're fine. So what you meant by that was just do like this, right? Is that right?
Yeah.
Okay. Then what? Remember the basic thing was e to the natural log of stuff equals the stuff again. So if I take the exponential of both sides of this equation, right? This gives me, oh, yowzers, x times x plus 3 equal to e to the power 10. So, you know, what's the difference between example 2 and the ones we worked out of like the MyLabs homework? MyLabs had like log base 6 or log base 2, things like that, and it had a small number on the other side. So when we exponentiated both sides, we got like 6 squared was 36 or something like that, right? Now we've got e raised to the power 10, which is just, well, I can tell you what it is, but you're not going to like it. It's 22,026.46579, right? What's that? No, it's not cute. But what is the case is that this is a quadratic equation, right? And so this is x squared plus 3x minus e to the 10th equals to 0. And this is one of those rare occasions where I advocate the use of the quadratic formula, because you're involving a large, ugly decimal number, and even if I complete the square here, it's not pretty because I end up with like 3/2 and such. I mean, I could still solve this by completing the square if you'd like, you know. Let's see here. Oh no, let's see here. So we've got x equal to, oh man, look at that. What? It was in the basket, it bounced out. I've never had that happen before. Like, that was bizarre. Now I was sure that was my fault. All right. Error marker. Okay, so we have x equal to minus 3 plus or minus the square root of 3 squared minus 4 times 1 times minus e to the power 10, right? All divided by 2, right? And we can work out what that is, yeah? If you do the math there, what you'll get, come on. Is working on it. Come on. So what that works out to is either 146.92 or minus 149.92. So the dominant expression there is the one under the radical, right? So like that radical is something like 9. Oh, let me get out of here. Ah! Turned it off by accident. Let me out. All right. 9 plus 4 times e to the 10th. So you got 88,114.86 under the square root. So like when you take the square root, this square root here, come on, this guy right here, this piece, is like 296.84, all right? And so like that's pretty much dominating what's going on here, that piece. So these are the answers. Now my question to you is, are they answers? See, because anytime we do this, we do this combining the log thing like we just did, right? We have to go back to the start and check our answers. So what do you think? Which one of these is actually going to work? One of them clearly does not work, right? Look at it. We've got log of x plus log of x plus 3, right? Can I put a negative number back into the original equation? I can't, right? So this one right here is extraneous. The natural log of minus 149.92 does not exist. You only have to, ruin one of the logs to count it out. But this one will work, and you can check it, right? You can try calculating what's the natural log of 146.92 plus the natural log of what? Add 3, right? So 149.92. I put that in my calculator, I add them, and if I take the natural log of 146.92 plus the natural log of 149.92, guess what I get? I get 9.999, 5 nines here after the decimal point, and then 0. So I think it's fairly clear that that one worked, right, up to the approximation that I've kept. Are we good? Let's do the other one. Example 3. Let me trace it again, because if you're back by the trash can, you probably can't even see this. Well, maybe you can. My eyes, not so much. Let's see here. 2 to the x squared. All right. So can we solve this? What do you guys think? How should we solve it?
Like, you find a common base. Or you can,
Oh, yeah. See, I mean, yeah, if this was like 9 to the x squared, I'd be right with you, right? Like example 4. This will be our example 4. Solve 3 to the 2x plus 1 equals 9 to the x squared. We'll do that one next, okay? That one we could do what you're saying. But this one, there's no way to make a 2 into a 3 unless you do something really, really like, I mean, I can do that, but that's just because I'm weird. You see, I just go, oh, sure, why not? 3 to the, log base 3 of x squared, of 2 to the x squared, which is, 3 to the x squared log base 3 of 2. And then I'm like, oh, okay, so then 2x plus 1 equals x squared times log base 3 of 2, by 1-to-1 property of 3 to the x, 3 to the x, I don't advocate you do it this way. That's really weird what I just did, right? Like that, I mean, you could do that, but no. I don't think that's the right way to do it, though. Like, what's the right way? And because 2 and 3, there's like, you've got the 2 and the 3, and there's really no natural way to convert 2 to 3, right? In terms of this math. So what I would do is I would just go straight from here, and I would take the natural log of the equation of both sides. All right? So that will give me natural log of 3 to the 2x plus 1 equals natural log of 2 to the x squared. And then what do I do? I think I've reached the point in the semester where I need to throw out all my markers. This one's not really working right either. So what should I do? Now what do I do? Well, now that I got that, we can make progress, right? So we can pull down by the power, by like law number 2, we can pull this out, right? And we can pull that out. And so this gives us 2x plus 1 times the natural log of 3 equals x squared times the natural log of 2, right? And then, oh, we've got a quadratic equation in x squared again, right? And this is definitely an ugly one. So here we go. Natural log of 2 times x squared minus 2 log 3 of x minus log 3 equals to 0. Did you guys see what I did there? What did I do? Oh, man. Uh-oh. Let's kick the wires back here. That's never a good thing. Yeah. Let's see here. All right, so this is a quadratic equation, right? It's not a terribly pretty one, but we can use the quadratic formula again to solve this. X equals 2 log 3 plus or minus the square root of 2 log 3 quantity squared minus 4 times the log of 2 times minus the log of 3. All divided by 2 times the log of 2, right? So I'm using the quadratic formula here. What is it? Is it this step, or? Because what I did was I put everything over here and then just flipped it. But like this is 2x log 3, so I subtract to the other side. Then 1 times log 3 gives me a log 3. I subtract it to the other side, and then I just put the 0. And, yeah. I try not to write below like here on the board because bad things happen with my handwriting. Okay, so yeah, whatever that is, right? Let's find out. So we've got log 2 for A minus 2 log 3 for B, and my C was minus log 3. That gives, when you work it out, approximately 3.609, or minus 0.439. I guess I should have kept another digit on the other one. 3.6091 there. Now I think in this case, they both of the solutions are going to work. Yeah. So here there was we never made a step where we were like combining logarithms. So I'm pretty sure both of these answers are going to be real answers. I mean, you can try them out, right? Like, let me try it out. Oops. So like if I take, 3.609 and I multiply it by 2 and I add 1 to that, that gives me like 8.218. And if I take 3 to the 8.218, what do I get? Three to the 8.218, I get 80, you guys have to remember this number, 8,336, okay? On the other hand, if I take 2 to the 3.609 squared, I get 8,334.5. So those are the same essentially. Not like I plugged the positive one into the equation on top. Both of them work out to about 8,335 or so. So the first one worked, and you can check the other one, it'll work as well. So, you know, are these pretty? No, right? But outside of the homework that's, you know, the homework that you've been asked to work for points, right? It's carefully constructed to have nice answers, right? So you should be grateful for that, right? I know you, I mean, I think sometimes we take for granted the things that are right in front of us that are, you know, gifts. See, because in the wild, these problems turn out much, much nastier. Yeah. Okay, anyway, enough about that. Do you guys have any questions about the homework? No? All right, well, I will forge ahead and work more of them then. Let's see here. I don't think we did.
You put that fourth example.
What's that? Oh, the fourth example. Thank you. What happened?
Where'd it go? It's under. It was like the sixth one of those little bugs I've seen. I've never seen those where I'm from. What is that?
Oh, you got the silverfish in here or whatever? Are they kind of skinny and fast? I used to have a lot of problems with fruit flies in classes. It appear in my course evaluation, be like, professor is usually distractible, always chasing fruit flies. I'm like, it's true, but they're annoying, you know? And fruit flies are different. When you're teaching by the biology's cat cadaver lab, fruit flies are different because then you have to ask yourself the question, where's the fruit fly been? You know? It's different. Oh man, look at this board. This board is just, God. Look at this. See, the problem is they clean the board with water, which leaves like a residue. The only way to get that residue off is with this stuff, of which I'm almost out. So this will be the sole board I can clean right now. There we go. All right, so how should we solve this other problem? Unlike example 3, we can convert 9 to 3, right? It's naturally 3 squared, right? So here we're looking at 3 squared to the x squared, yeah? And then by laws of exponents, what we have is 3 to the 2x plus 1 equals 3 to the 2 times x squared, right? And then we can use the one-to-one property of the 3 to the x function, right? So by the one-to-one property, this implies 2x plus 1 equal to 2x squared, which is still slightly unpleasant, but not so unpleasant, right? So here we've got 2x squared minus 2x minus 1 equals to 0, yeah? And maybe we can solve that, right? I'm not sure it factors. I mean, we could try. You want me to try? So I can either do like plus 1 minus 1 or minus 1 plus 1 here. If I do plus 1 minus 1, that gives me like a plus x in the middle. And if I do the other way around, I get a minus x. And there's no way I can get the 2 in the middle from factoring. Yeah? So that doesn't work. So how should we solve this then? I can't factor it. What do we do? Well, what I would do is, I mean, you can either fall back on the quadratic formula, right? But this one I can complete the square on without too much trouble. So this is x squared minus x minus 1/2 equals to 0, right? So that's x minus 1/2 quantity squared minus 1/4 minus 1/2 equals to 0, which gives me x minus 1/2 squared equals to, and what's a quarter plus a half? A quarter plus a half is 3/4, right? But it's a minus 3/4 on the left-hand side. So if I move the minus 3/4 to the other side, I get instead of minus, I get plus 3/4, right? And then take the square root of both sides. I get x minus 1/2 equals to plus or minus the square root of 3/4, which then finally gives me the solution of x is equal to 1/2 plus or minus the square root of 3/2. Which of course is also what you would have obtained from applying the quadratic formula there if you wanted to. So I would hope I could put example 4 on a test without regret. You know? Example 3, like example 3 is just a little bit ugly. It would not be a pleasant experience to grade this problem on a test, but it is nevertheless a problem you should be able to solve, but it is, granted, it's ugly. I do try to make a good subset of my test questions work out so they're not ugly, right? It's a general point of order. But anyway, any questions? Okay, so let me work another problem here. This one's like number 23. Did I already talk about the Richter scale in here? I can't remember. Oh, I got to talk about that then. I'll get back to that next. Those problems are not bad. There's like a couple word problems on decibels early in the homework. Those are harmless, but I need to talk about them. Log 3. And whenever we see log without a base, what log is it? 10, right? Very good. It's the common log, right? All right, so how are we going to solve this one? So this one's a little bit different. I think the simplest way to solve this one is as follows. I take these two, right? So first of all, I can't do anything with it as it's given to us. There's no nice way to like just draw something from this equation directly. However, if I combine the two logs on the left-hand side, which I can do, right? That's log of what? 4x plus 3 times 3, right? Now I've got log of something equals to log of something else, right? And it's the same base, log base 10 both sides. Here's the thing. If a function is 1-to-1, its inverse is also 1-to-1, right? In other words, the log is a function which has the 1-to-1 property because 10 to the x has the 1-to-1 property. Anyway, my point to you is that we can equate the inputs of both of the logs if we get like this. If you want, we could raise both sides to the 10 power. You know, if you want to see it that way, we could do that. Right? If I do 10 to the log, I get 10 to the log, right? Both sides. But the log and 10 to the something and log of that, these are inverse functions. And so what we get is 4x plus 3 times 3 is equal to 11x plus 12, right? And of course, you could have multiplied this out already, right? Let's do that now. So we got what? 12x plus 9 equals to 11x plus 12. Subtract 11 with the other side, we get x equals to 12 minus 9, which is to say x equals to 3. I think it's kind of funny. This problem looks scarier at the start, but I think actually this is a significantly easier problem than the last two we just worked, right? It's in my book, it's easier when after you get through the logs or the exponentials or whatever, if you find yourself facing a linear equation, that's an easier thing to do than when you get to a quadratic equation and you have to sort through two answers and so forth. All right, let me go back to the decibel problems. Does anybody know about decibel measurement? Have you ever heard decibel before? Maybe? So a lot of times people measure like the loudness of speakers or something in decibels. If you ever bought an antenna, it might have like a dB rating. And so decibel is a logarithmic scale kind of thing. And so here I'll work number 5 here. So we're told that D is equal to 10 log of I over I sub 0, right? And then it says if the sound has I equal to 10,000 times I sub 0, right? Then what's the decibel rating of such a sound? Now I sub 0 is like a standard reference sound. And we could not come to an agreement about what that should be in my other section of college algebra. Well, I eventually settled on the following principle that like a reasonable, if you were in, medieval times or perhaps ancient times, you remember that we used to define the unit of measurement by like a cubit, right? And cubit's like the length from your middle finger, I think, to your elbow, right? If you've ever been to the Ark experience, there's like to talk about this because they built the Ark on the basis like number of cubits in the Bible, right? So what that actually means, it depends on how big your king was, right? So if you had a tiny king, you'd have a tiny ark. If you had a big king, you'd have a bigger ark. I think they chose a bigger king to make it more fun. I don't know. So I said, well, maybe I sub naught is like it's the intensity of your king yelling at you from 10 feet away or something his loudest. Maybe that's I sub naught. This is the reference. This right here is just a reference intensity. So like it's not really told in the problem what that is. It's just some reference point for sound intensity. All these decibel ratings are done like this. There's some kind of standard, there's some sort of hypothetical standard things are held to and compared to. So like decibel ratings are always a measure of some sort of relative intensity of something, all right? For example, you could judge the energy per square meter time that you're getting from light in here. That's called the intensity of light, right? And then you could compare the intensity of light in this room to like the intensity of light outside on a sunny day. How many times do you think, if you had to guess, like how much brighter do you think it is outside than in here? So popular guesses up to this point in my other classes have been like 4, 5, 6, maybe 15, 10. The right answer is something like 10,000. Like, I don't think, like a sunny day, there is so much more energy in the sunlight outside than in these lights. And that's why something like a dB rating is useful, because a decibel rating is useful. Log scale is useful because of this, guys. If we take log of, say, 1,000,000, and we take log of, say, 10, what's log of 1,000,000? Well, it's 10 to the 6th, right? So it's 6 here, right? Log of 10 is 1. So see, we can compare numbers from, say, 10 to 1,000,000 by just using numbers from 1 to 6. So it's a way of comparing numbers over vast arrays of magnitudes all at once on one nice scale. Like this is the point of a logarithmic scale, is it gives us some sort of intuitively accessible way of comparing different magnitudes. But you have to be careful, of course, because if you think about that in terms of like linear things, like you might think, well anyway, my point is just this logarithmic scale we have. Well, let's see how this works out. What I'm about to say will be borne out in this example here. So what is the decibel rating for number 5? This is part A. We just have to plug this formula that we're given into the decibel rating formula, and what's that give us? So we got 10,000 I naught divided by I naught equal to. So the I naughts cancel, which is this is why they didn't have to tell you what it actually was. And you've got 10 log of, what is 10,000? Well, 1, 2, 3, 4 zeros, so it's 10 to the fourth. So this is 10 times 4. So the answer for part A, for my number 5, is 40. You got a decibel rating of 40. And then the question is this: if you tripled the intensity, what would the dB rating be? What would the decibel rating be if you triple it? So let's say, suppose I2 is equal to 30,000 I naught, right? Then what's the, by how much does D increase? That was increase. You guys are going to ask about the spelling of that. Increase. 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 All right, okay. So D2, we just plug in 30,000. What happens then? So again, the I naughts cancel, and we get 10 log of 30,000, right? So I could rewrite that as log of 3 plus the log of 10,000, yeah? Of course, you could just plug the 10,000. You could just take log of 30,000 directly in your calculator if you want. I mean, it's fine. I'm just trying to I'm just trying to get a little bit more mileage out of this problem in terms of exploring log properties. But notice that we've got 10 times the log of 10,000 here. We already worked that number out in part A, right? And so 10 times log of 10,000, that's 40 from the previous part of the problem, right? This is the 40 that we already had. Yeah? Ooh. And this is the extra, right? From the last part. Oh well. So then the question is, what is that extra bit? I think it's 4.471. Let me try it though. 10 times log of 3 is 4.771. So we've got 4.771 plus 40, which of course gives me 44.771. So there is the, now that's not the answer to part B, because what was the question? The question, right, was how much is the decibel rating increased? So to answer this question, I need D2 minus the original D, right? Which is like 44.77 minus 40, which is, 4.77. That's how much it's increased, right? But then that still would be wrong if you put it into your homework, because what does the homework ask you for in part 5? It says right under part B, it says round to the nearest integer as needed. So then what do I got to do? The answer should be what? The answer here is 5, right? So now your problem might be a little bit different, but that's how this one goes. So problem 6 is pretty much the same kind of problem. It's just instead of being about decibel rating of sound, it's about the Richter scale. So like, you ever heard of earthquakes? So in my problem 6, I'm given, a hypothetical earthquake is measured on a seismograph, and you're asked to calculate the Richter scale. Yep.
Why did you have to do this extra step? If you already had the 4.771 plus the 40, and you turn around and minus the 40, why did you have to add the 40? Why couldn't you just kept the 4.771 and then added that up to 5?
Oh, I could have if I had interpreted it that way. If I had just been like, oh, okay, so this is what I had before, therefore this is the increase. The answer should be it's increasing by 10 log 3. I'm totally on board with that. But I would say for the people there's some people who watch what I'm doing, and maybe they just think, at this point right here, I should just stop and go, well, the log of 30,000 times 10, right? For those people, they got to go over here and do, log of 30,000 is 44.77, and then I have to subtract apart from the previous problem. I'm just trying to emphasize it's on the increase, but you're absolutely right that the answer really is this piece right here, rounded up to 5. So in short, my answer to your question is I wasn't being lazy enough. So I could have been lazier. I didn't need to write the purple thing. I could have just put a box around that and said, that's the answer, Absolutely. Rounded, of course, I have to round it. But. All right, so another problem which I think might give you guys some fits. I don't think I've done this one in here yet, so let's do it. It's kind of a little bit weird. The format of the question's weird, so let me fuss with this one here with you guys. Did I talk about the Newton's law of cooling in here? See, the thing that's really messing with my head, guys, is not only am I teaching 4 sections of this class, one of the other sections is also in this room. So I have physical memory of working problems in this room. And sometimes I'm thinking of you guys, right? Sometimes I'm thinking of that other section. So this is why, well, anyway. Okay. Example 7, we're told to let u equal natural log of a, and we're going to let v equal natural log of b, and then you're supposed to simplify expression below using u and v. All right. So you've got natural log, this is given in the problem, natural log of the square root. By the way, this is like number 8 in the week 12 homework. Natural log of a squared over b cubed. So I like this. This is a good problem. It's a solid question, I think. So I tried to go over it in all the sections of this class because I think there's just a lot of goodness on this problem. It's not too hard. It really emphasizes some of the major things we've learned. So let's go through it. So natural log, first of all, square root is a squared over b cubed to what power? When I take a square root of something, what is the fractional power that corresponds to? 1/2, right? Then what can I do? So by the property 2 of the log that we proved last time, right, I can pull the half out, yeah? So I get 1/2 log of a squared over b cubed, right? Then what? Well, now I can use the property 3 of the, like the logs, that the log of a fraction is the log of the numerator minus the log of the denominator. Keep the half out front. So I've got log of a squared minus log of b cubed, right? And then what? What can I do? I'm still not to things. I need to simplify it down until I've got log a and log b, right? So I'm not there yet. What do I need to do next? So I've got log of a squared, right? So I can pull this 2 out. I can pull this 3 out, right? By the same property I used going from like this one to this one. All right, so this is 1/2 2 log a minus 3 log b, right? And then what? Just multiply the half through, right? So the half and the 2 cancel, we get what? We get log a minus 3/2 log b. So what would the answer be then? Uh-oh. Phew. Ah, come on. Yep, answer has to be given in terms of u and v. that is the answer. So I would say don't be intimidated by that problem. It's not actually that hard. But let's see here. Let's see. Another one we could work would be. Did I work number 15 in here yet? I don't think I did. It might, well, I'm not sure if I worked this or not. Well, I guess I shouldn't work. Number 15 is more or less. Number 15 in your homework would be like example 1 from today or example 2 from today. I can't remember which, but one or the other. Let me see here. This works. Other ones I haven't done. I did not? All right. Well, we can do that one then. Okay, so 15 will work then. So my 15 looks like this. 3 times 1.21 to the x plus 1 equals to 15. This is my number 15. 15's got a 15 in it. That's weird. All right. How do you solve this? Well, subtract 1 to the other side would be what I would do. And then I would have 3 times 1.21 to the x equals to 14. And then I suppose if we divide by 3, that's kind of like the nicest way to do this one. 1.21 to the x equals to 14 over 3. And then I'll just hit both sides with the natural log, and that'll give me the answer basically. So natural log 1.21 to the x power equals to, natural log of 14 over 3, which gives me x times the natural log of 1.21 equals to log of 14 over 3. Then solve for x. X is equal to natural log of 14 over 3 divided by the natural log of 1.21, which, of course, we can obtain a decimal approximation for if we want. Let's see here. So I get, come on, marker, 8.0812. Let's see here. I don't remember how many digits the problem asked for. Nearest thousandth as needed. So I don't need the 2. That would be the 10,000th place. So the answer would be this for the homework. So there you go. It's number 15. If you guys want me to work another particular one, just speak up. Otherwise, I think I'm going to jump to the very end. There's a couple problems towards the very end which are a little bit different. Yep.
Are you going to always ask for that problem in decimal form?
I will ask for decimal form sometimes. Sometimes I'll ask for both. Like I might ask for, an exact answer and its decimal form rounded to the nearest thousandth. I can't say thousandth. So it depends. I mean, sometimes I want both. Let's see here. There are advantages to asking for the decimal form, just in terms of clarity for me as I'm grading, because there are like a lot of different ways to write an answer using logarithms. Like I took the natural log of this equation, right? But I could just as well have, for example, a very different path you could have gone here would be to take log base 3 of both sides, right? And then when you did that, so that gives you x times log base 3 of 1.21, this is 1, equals to log base 3 of 14 minus 1. X is equal to log base 3 of 14 minus 1 over log base 3 of 1.21. So, you know, if you ask a question like this and then you say, I want an exact answer in terms of logs, you open yourself up to requiring a lot of different kinds of thinking. There's a lot of different ways to write the exact answer, but they should all have the same decimal approximation, right? So if I had used log base 1.21, it would have looked even different, you know? Anyway, I digress. Here's number 28. So I think we solved a good swath of the equation problems in here. So I'm going to shift over, look at a couple of symbolic problems at the end. Everybody top hatted already? Let's see here. Okay, here's one. So I'm asked, I'm given P equals to K over the natural log of W minus C. All right? And it says solve for W. So some of you are taking this class in order to have it as a prerequisite for like Physics 201, right? Maybe not in here, but there are students who do that. And so like this is the kind of algebra problem you might end up running up against in Physics 201, possibly. Probably not, but anyway, these kind of algebraic problems appear in like physics and engineering, things like that. How do you solve for W? What do you think we should do? I'll do the easy thing. Add C to both sides, right? Yeah, add C. So P plus C is equal to K over the natural log of W. So the answer, right, the answer here is going to be in terms of the P, the C, and the K. Right? These are just variables. They're unknowns. We're not given their values. The answer is going to involve the constants P and K and C, all right? Multiply by K. Oh, okay, so like, well, we could do this, right? We could write natural log of W equals to K over P plus C. Would you agree, or? Does that make sense to you guys? So basically kind of like a cross multiplying step of sorts. And then now that I've got natural log of W isolated, what can I do? How do you kill a natural log? What's the rule? Remember, E to the natural log of W equals to what? It equals to W again, right? So if I exponentiate both sides, I think that'll do it for us. So we have E to the ln of W equals to E to the K divided by P plus C. It's kind of ugly, but there it is. And so this gives us W is equal to E to the K over P plus C. And that's the answer for mine. Yours might be actually, I think these might not be randomized. I may have accidentally just worked your number 28. This may just literally be your number 28, and so if I have actually worked your only homework problem, my apologies. But the important thing here, of course, is not the answer. The important thing really more is the steps, right? So you want to understand the steps, understand the philosophy of what you're trying to do, which is to isolate the variable you're solving for, right? So problem number 29, look at that one next here. So here we're given the equation t equals to t sub 0 plus big T sub 1 minus big T sub 0 times 7 to the minus k little t. All right, and we're supposed to solve this for little t. So just to give you context here before we do any of the algebra, the way to think about these letters is this is like temperature, and T is time. And this formula we're working with, it's actually the equation for Newton's law of cooling. Do you guys know Newton's law of cooling? So what Newton's law of cooling says is that if you have some object, the rate of change of temperature for that object is proportional to the difference between the temperature of the object, which is cooling, and the room temperature. So if you look at this equation, if you look at it, T goes to T sub 0 as little t goes to infinity. Because assuming here k is positive, so if k is positive, what happens with 7 to the minus kt is it gets really, really small for large time. So what does 7 to the minus kt look like if k is positive? The graph of that is something like this, right? So as t goes to infinity, 7 to the minus kt goes to 0. This stuff drops out, right? And the formula here eventually just goes to T sub 0. So T sub 0 is the room temperature. It's the ambient temperature of the system. In contrast, if we plug in time equal to 0, what happens? T equals to T0 plus T1 minus T0. See, because e to the 0, 7 to the 0 is 1, right? So at time 0, you get T1, right? So basically, what this formula means, you can think about it as it applies to, say, a cup of hot coffee. T1 would be the initial temperature of the hot coffee, right? And then if you leave it out in a room, which is 70 degrees, eventually its final temperature after a long time will be 70 degrees, right? We've all experienced this. Or do you guys have one of those self-heating cups? Do you know about these? There's a mug you can get that heats the coffee continuously. It's battery powered and such, of course. But I do not have such a cup. But if you have so you're thinking about what to get Dad for Christmas, right? Does your dad have this cup? Because if he doesn't, it would be an awesome gift. I don't know how much they are though. I don't know. Okay, so how do you solve for t then? Now I've given you the backstory of this equation. It has nothing to do with the problem. I just wanted to let you know why this is an interesting equation. I think first thing we should do is to subtract t naught from both sides. And so we get big T minus big T naught equals to T1 minus big T naught times 7 to the minus kt, right? So our goal is to isolate little t, right? So the next thing I would do would be to divide by that coefficient in front. So this gives me t minus t naught divided by t1 minus t naught equals 7 to the minus kt, right? I've almost isolated little t now. What can I do next? I could take natural log, right? But I think the better choice here is to take log base what? Yeah, log base 7. I think that's a good choice. So log base 7 on both sides, what do we get?